Another property is intersect all the asymptotes. It called as also centroid, because it gives us the center of the gravity of the root locus. It can be found with this formula. Sigma 1 will be equal to poles O GSHS minus the sum of zeros O GSHS over by n minus m, and it can be defined as 17. What is mean? Maybe we should do an example here. We have a system as s plus 2, s plus 3, plus k times s plus 1 will be equal to 0. So we can find GSHS as k s plus 1 over by s plus 2, s plus 3. So let's draw the S-plane now. Real axis and imaginary axis. Let's define the poles and zeros for this function. We have a pole at 0, 1, 2, and 3. At 1 we have a 0, 2 we have a pole, 3 we have a pole. Okay, poles are always signed with times symbol, and zeros will be a circle on the S-plane. If you draw the root locus of this system, one of it will be start from this pole to this 0, and the other of them we should find the intersect of the asymptotes. What is it? For this system is here we have the open loop transfer function. If you use equation 12, we will get the asymptote intersect of the asymptotes. Sigma 1 will be equal to the sum of the poles, which is 0, minus 2, and minus 3, minus sum of zeros, which is minus 1 only, over by n minus m. N is 3 here, and m is 1. So we will get minus 4 over 2 minus 2. Okay, so at minus 2 we have an asymptote as like that. Another pole will start this pole to this direction and this pole to this direction. It will continue as like that, and the symmetry of it is like that. Okay, when k approaches to infinity. This is the asymptote for this system. Okay, let's do another example about the asymptotes. Gs times hs is given as k s plus 1, s plus 4, s squared 2s plus 2. Okay, for this system, let me find the asymptotes of the system and pole 0 placement on the S-plane. What we get, what we have as an angle, so the asymptotes. Let me find all of these parts for this question. Okay, GS, HS as given as like that. So we have a 0 as minus 1, poles 0, SP2 is minus 4, SP3 and 4 is complex conjugate, as you see, minus 1 plus m minus j 1. What is the intersection on the asymptotes? We can find it with this formula 17, as you see. The sum of the poles minus sum of the zeros over n minus 1. So we get minus 4 minus 1 minus 1. Complex part will be eliminated. Minus 1 over by, we have 4 poles and 1 0. We'll get minus 5 over 3. We get as approximately 1.67. This is the intersection of the asymptotes. What about the theta asymptote angles? As you see here, we can find the angles with the equation 16. Theta 0 is, for K0, we have 180 degrees over by 4 minus 1. We get 60 degrees. For theta 1, 3 times 180 degrees over by 3 again, we get 100 degrees. For theta 2, 5 times 180 degrees over by 3, we will get 300 degrees. We have, how many poles we have? System order is 4, as we see. So we will have 4 branch for this system. So we should also theta 3, 7 times 180 degrees over by 3, we will get 60 degrees again. Okay, so how can we show it on the diagram? We have a pole at the origin, minus 1, minus 2, minus 3, and minus 4. We have a pole at minus 4, j, minus j. We have another pole here and here. So we have 4 pole and a 0 at minus 1, as we see on the system. So what we have as an asymptote and intersection of it, assume that 1.67 is approximately at this point. The asymptotes of the system will be as like that, and also as like that. Those are the asymptotes, which means k approaches to infinity. Okay, what about the theta? 60 degrees, 180 degrees, and 300 degrees. As we see here again, in the asymptotes, we have also a symmetry property. Okay, another important property is root locus on the real axis. On a given section, of the real axis, RL for k equivalent greater than 0 are found in the section only if the, it's important, only if the total number of poles and zeros OGSHS to the right of the section is odd number. This is the rule to specify which section to be included, which section will be not. For example, GSHS will be given as S plus 2, S plus 4 over by S plus 1, S plus 3, S plus 0.5 plus J, S plus 0.5 minus J. This is the system. Let's draw the S-plane and show it on the S-plane. Assume that 0.5, 1, 2, 3, and 4. Okay. Let's assign the poles and zeros on the S-plane. We have a pole at this point. We have a pole at -1, -3. We have a 0 at -2 and another 0 at the -4. Let's evaluate this section, this point. If we see on the real axis from here, we cannot see any poles and zeros. It means we have 0 poles and 0 if we see at this point. So this point or this section will not be included. Okay, if we choose this point and if we see right side of the S-plane, we can see one pole. It's an odd number, so this part will be included by the, maybe we should use another, yes, if we see right side on the S-plane, we can see one pole. It's an odd number, so this part will be included by the RL. If we see at this point to the right side, we can see 1 0 and 1 pole. It means we have 2. It's an even number. This part will not be included. If we see at this point to the right side, we will see 3. The total number which includes 2 poles and 1 0. So this part will also be included by the RL. Okay, this is the rule. Let's see another important property of the RL, intersection of the RL with the imaginary axis. For this topic, we can use Routh-Hurwitz method. Routh-Hurwitz criterion or method may be used to find the intersection of the root locus on the imaginary axis. Why we need it? Before this, maybe we should talk about it. Why we need to find the point intersection with the imaginary axis? Because, as we know, this is the limit for the stability. Imaginary axis is limit for the stability. If we pass the imaginary axis, it means right half as plane, unstable system. And if we pass to the left side, this is the stable system. So we should find the k value for the stability, limit of the k value for the stability. Let's do an example. S plus 3 s squared 2s plus 2 plus k is 0. This is the characteristic equation. Okay, if we expand this expression, we will get s to the power of 4 plus 5s to the power of 3 plus 8s to the power of 2 plus 6s plus k will be 0. Let's remember the Rutherford criterion. We have some sufficient condition, necessary condition, and sufficient condition. Necessary condition can be satisfied if k chosen as greater than 0. Then we can use the Rutherford's table. S to the power of 4, 3, 2, 1, and 0. Yes, 1, 8, and k. This line will be 5, 6, and 0. So at this point we will get 40 minus 6 over 5. At this point we have k. This column will be 0, as you know. This will be approximately 6.8. What about this row? 6.8 times with 6 minus 5k over by 6.8. This point will be 0 and 0 and will be k. So the k value in this row, before this, maybe we should remember the stability condition. All parts of the first column should be the same sign and there is no sign changing. This is the necessary for the stability. What if we are curious about the limit of the stability, or if we want to find the exact value of k where we have a pole at the imaginary axis? To do this, we should have at least one row as 0. So it is possible to choose this row as 0 for the marginal stability. 40.8 minus 5k should be greater than 0. So k should be less than 8.16. Okay. If we choose k as 8.16, it means the system is on imaginary axis. For this expression, if we find the s value, okay, to find the pose at for k is 8.16, we can use auxiliary row. How can we write it? 6.8 8 times s squared plus k will be 0. S will be, if you do this operation, plus and minus 1.j 1.0 9 and 5. 9 and 5. So the intersection of the root locus with the imaginary axis will be found as like that. Okay, the new topic is breakaway point. On the root locus, of course. How can we find these points? For any root locus, it may have more than one breakaway points. Breakaway points may be complex conjugate in the S-plane. We should know it. How can we find it? We will use dg1s, h1s to ds set to 0. It gives us the breakaway points. Let's consider the system as s plus 2 plus k s plus 4 will be equal to 0. What we have as g1s and g2s, gs, hs will be equal to ks plus 4 times, over s times s plus 2. So for this system, g1s, h1s will be s plus 4 over s times s plus 2. Differentiate of this equation. S times s plus 2 minus s plus 4 2s plus 2 over by s squared plus 2s to power of 2 set to 0. And we will get s squared plus 2s minus 2s squared minus 2s minus 8s minus 8 will be 0, minus s squared minus 8s minus 8 will be 0. So the roots can be found as s1 minus 1.172, s2 will be minus 6, 8, 2 and 6. This is the breakaway points on the root locus. Maybe we should draw it. We have a pole at origin, minus 1, minus 2, minus 3 and minus 4. We have a pole at minus 2, a 0, minus 4. So this section will be included. Yes, this section will be included. This section will not be included, and this section, which we goes to here, will also be included by the root locus, as we know before. So start from a pole and another pole. What we have as a breakaway point, minus 1.172, approximately here we can accept it. Here we have a breakaway point, and it will go as like that, and it will, another breakaway point is here, minus 6.728. It will goes to this point. Maybe we can draw it as like that. Of course, to draw this, I will use my experience. One of the root will goes to 0 and another will goes to infinity. K will be goes to infinity.